Swarms of robots can reach areas that are inaccessible to humans. Here, for example, they can fly over a forest on fire. By following simple rules, the robots can collectively monitor the environment and select the most important site. The environment can suddenly change, and the robot must reconsider its decision about the most important site. We studied this problem with a swarm of kilobots that move on a table and exchange minimal infrared messages with one another. Robots can estimate the importance or quality of a site from a distance of 20 cm as indicated by the superimposed colored circles. Each robot only exchanges the site's location but independently estimates the site's quality before broadcasting recruitment messages. Robots periodically select one random message from their neighborhood and use it to update their opinion, a protocol known as the voter model. Robots transmit the location of their preferred site with a frequency proportional to the estimated quality. In this way, better sites are favored. In this example, the swarm reaches a consensus in favor of the blue site. Imagine the swarm has reached a consensus, but a better site appears. Can the swarm adapt? We studied the adaptation of the swarm to environmental changes, and we found something counterintuitive. The smaller the robot's communication range, the better the swarm coordinates its response to the change. The swarm with a global range of communication, in which any robot can communicate with any other, did not adapt to the change, even after 40 minutes of experiment. Instead, when we limited the interaction range of the robots to 10 cm, corresponding to 3 body lengths, the swarm always successfully adapted to 3 types of changes. The first type is the appearance of a new, better site. In this experiment, we can see the swarm reach the consensus in favor of the red site. The second type of change is the disappearance of the best site. Also in this case, the swarm is able to modify its decision for the best available site. A third type of change is when the quality of 2 sites is exchanged. In this experiment, the green option just became the best site, and our swarm quickly reacted to such a change. Despite robots making noisy estimate and relying on simple communication, the swarm quickly reaches an agreement on the best site. It's natural to wonder, why does a short communication range help the swarm to adapt to changes? We see that at the moment of a change, there is a minority of robots that discover a new, better site, in this example, the red site. How do the minority convince a majority to abandon their previous option? The minority has found a better site, therefore communicates more frequently. However, when communication is global, the new information held by a minority does not spread. Our mathematical model shows that when the minority-majority sides are unbalanced, there are few versus many, small neighborhoods are beneficial. Less social information gives the robots the possibility to listen to minorities and consider their opinion. Instead, when social information is too abundant, a minority of robots, even if more opinionated, cannot overturn the less active majority. Exploiting the advantages of a local communication range for group coordination can also be observed in social insects from which our robot behavior is inspired. Modeling and understanding collective robotic systems is necessary to design efficient algorithms. Our analysis shows when less social information can give more environmental adaptation, an effect known as less is more.